And I'm going to be talking today about recommender systems. And we had 3 topics on NLP, 1 topic on image classification, and I'm going to cover the other category on recommender systems in e-commerce. In case you want to follow the slides independently, you want to go back, you can use this QR code, and then you'll just get the link to the presentation. And with this link, you can just go back and forth, and in case you want to check something up. So my project is going to be about recommender systems in e-commerce, which is a more or less general topic, but nonetheless really relevant. And I'm going to be particularly exploring the 2-tower deep neural network architecture and its application on actual industrial data. First of all, maybe a short introduction why recommender systems are still really important nowadays, especially B2C companies. For them, it's a thing that is almost indispensable. That's really the best tool that they can use to combat user churn and to grow their customer base. At the same time, these systems are highly dependent on data, as everything else in data science and machine learning. So the better data you have, the better your recommendation system is. And because the recommendation task is so complicated, it's so dependent on the environment, generation of always constantly quality recommendations is a really hard thing to do. And I think everybody already noticed that if they get recommendations on Netflix or Amazon, you can also tell that these companies are not really perfect at it, because once in a while you might get something relevant, but you still get irrelevant recommendations from time to time. And this comes to the biggest challenges in recommendation system model design. There's really no ground truth. Nobody can tell what is a good recommendation. Nobody can tell what is a bad recommendation. I mean, only the person that actually is exposed to the recommendation can actually tell you that. And this makes this problem a little bit hard to tackle, because compared to other machine learning or deep learning problems like classifying cats and dogs or classifying handwritten digits as an example, there everybody can agree on a ground truth. Here, unfortunately, it's not the case. So this is something difficult. And that's why the model design has to take into account how actually this ground truth problem should be approached. Also, as I noted, the environment plays a really big factor. You can train your model, the model can perform really well, but let's say COVID happens tomorrow and all of your, the market goes down and your recommender system is really not performing that well anymore. So you have to retrain the model and you have to start again from scratch. And of course, probably also one of the most important things is that your recommender system, if it's not good, then it can generate bad recommendations. So it's actually going the other way, and it's not sustaining your customer base, but actually they're pushing it back from you. Because if you get bad recommendations, let's say you get a recommendation for a product that is out of stock or has bad reviews, probably you won't think much of the service that you're using, and you will probably eventually, if you get repeatedly these kind of recommendations, you'll go away from this e-commerce shop. What are the main approaches when it comes to tackle recommender or building recommendation systems? So let's just start with the simplest one, which is called content-based filtering. This is pretty much a non-scientific approach, which is completely bound to logical rules of logic, and it's just based on relationships between items that are recommended. So, for example, if somebody likes from category A, you can very likely recommend other items from category A that this user has not interacted with before. So for content-based filtering, really important is the relationship between the items to be recommended. For collaborative filtering, which is a more advanced approach, you use also the similarities between the customers or the users, which means that if users share similarity like demographics, income, age, etc., sex, maybe it could be also a good feature to incorporate into your recommendation system. So you're actually going there both ways. You're getting the feature space for the items recommended and also for the customers as well. And one of the things that collaborative filtering is working really well with is matrix factorization, which is nothing more than just a mathematical operation on the embeddings that the customer or the user gets into along with the items. The dot product gets calculated, and the dot product is basically the formula for generating a score, kind of like a metric for items to be recommended or not. It will become clear if I show a couple of examples. For content-based filtering, as I said, This is a pretty much no-brainer. You have one feature. In our case, we're talking about music. In this example, we have a feature called genre, pop, jazz, rock music. And let's say a music listener is into a specific music genre. Then you can actually also map potential recommendation candidates to this feature, which is, in our case, is the music genre. And you can just translate it to what the recommendation for this music listener could be. For collaborative filtering with a matrix factorization approach, this can be more advanced. You can have really way more features. And with these features, you build a so-called embedding space. This embedding space you can quantify as you like. In our example, we are just going to stay with the music example. We have energetic music or calm music as one embedding space, and the other embedding space is more instrumental, more emotional, lyrical music, and more instrumental music. And what you could do, you could map both the music listeners, and you can map also the recommendation candidates into this feature space. And this creates a kind of like positioning in that embedding space, which is then calculatable through a dot product. So what you essentially have is a user vector, and you have a candidate vector. And these vectors, they get multiplied through a dot product, and the score then gets calculated for each interaction that the music listener, in our case, and the candidate have. And the highest score is then could be possibly your recommendation that you can actually go with for our example. So these were kind of the trivial approaches how we tackle recommender system problems. Nowadays, there is a more well-established approach when it comes to deep learning. It's called the two-tower deep neural network approach. And this is actually nothing more than just extending the matrix factorization to deep learning, making it more learnable in terms of nonlinearities and catching features that go just beyond the dot product calculation. So how does it work? We basically have two neural networks, and one stands for two dimensions. The first is the query tower, which is basically representing the customer or the music listener from our previous example, or could be a user on a website as well. And everything in that neural network represents an embedding that stands for the customer. On the other side, we have the candidate tower, which is basically what are we going to recommend to this customer. And it's exactly the same logic. We have embeddings. These embeddings get concatenated into one big vector that represents one candidate, and it gets up into the neural network, where these neural networks meet in the dot product calculation. But at this step, this is not over yet. We're going up, and we go into the optimizer, where we go through several hidden layers. This is a question of architecture design. It's completely up to you how you want to design it. And then we go into so-called in-batch softmax. So similarly, as in multi-class classification, we use the softmax as a loss function. But here for the recommendation part, we're using a so-called in-batch softmax, which uses a more sophisticated approach of frequency sampling for your candidates to calculate probabilities that are going to be then mapped against the true pairs that the candidate and the query interacted with. So through that, you can actually then calculate your accuracy and optimize. What happens then when you build your model, you train your model? What you could do to make predictions is through a so-called retrieval process. So it's also pretty straightforward. You have your customer in this case. You compute a query out of it. So you compute a vector, and then you just feed that vector into the model. And then basically in that embedding space, it's more or less like a lookup table. The lookup table returns you a recommendation. And these recommendations are quite flexible. You can compute them as wide as you want. You can do a top 1, top 10, top 100 recommendations. It all depends on the calculated softmax. And if you hook on more nonlinear dense layers, then you can actually also learn nonlinearities, which is actually then really, really advanced and not possible with the previous approaches that I touched upon. Now, coming actually to the practical side of things, my portfolio project where I worked with live industrial data. The data is for a beauty care from the beauty care industry and was kindly provided by a leading online retailer in the beauty sector. The data consists of about 6.7 thousand unique products, excluding product variations, and about 250,000 customers that were time-stamped and represent the full year of data. So, and I already have the split between the customer and the product for the reason that, as probably you can already sense, because we're going to build a two-tower neural network. So we're going to have the customer on one side, and we're going to have the product on the other side. And for the product, we have also images that could be also used to feed into the neural network. For the customer, we received anonymous ID, timestamp of the interaction, and the interaction type itself. For the product, we had more features like brands, the series of the brand, the category, the gender of the product, the price, the volume, and many other attributes that could classify the product even further. So we have a slide, well, not a slide, we have actually a pretty huge feature imbalance between the two towers. And this is actually how it looks like then in the end, just the same, the two towers. One is for beauty product embeddings. So every single feature that I try to concatenate them and feed them into the neural network. And the same is for the customer tower. Build one vector, concatenate it, feed it up, and then optimize against it, and then generate recommendations. So now I'm going to go to the training part, which is might be a little bit tedious, but I think it's also important to guide you through how the recommendation system training process looks like, because one of the things that you have to do is you have to experiment and you have to feed in more features and see what's happening with your validation accuracy. So for the baseline model, I could also only say that we could just take 1 divided by 6,700, which is the total amount of our products that we have, and that will be our random baseline. But we don't want to do that. We want to be more advanced, and that's why the baseline model I'm going to take already have the two-tower neural network. The query tower, I'm just going to give the customer ID. And for the candidate tower, I'm just giving the product ID, nothing else. So no more additional features. And I'm going to see how my training and validation accuracy behaves. No surprise, big overfitting, but still validation accuracy is at 20%, which for the baseline model is actually not that bad. Here, we are not utilizing a deep neural network approach. Actually, we are. We have one hidden layer as the output, but this is more a requirement for the network to work. But in that hidden layer, we don't have any nonlinear activation functions. So it's just a loss function, an optimizer that optimizes the embeddings with no activation for nonlinearities like ReLU or 10H. So let's start to add more features. So for the customer tower. So the candidate tower is still void. We still have only the product ID, and now we're adding more interaction type, the timestamp of the interaction with the product in normalized and in discrete form. And let's see what happens with our training and validation accuracy. And we can actually say that the baseline model is not is still the best model in this case, because adding more features does not really do good for the training or validation accuracy. We're still at the setup that we have only one hidden layer, no nonlinear activations, and we can already conclude that we have all the features in the query tower, but our model is actually not performing well. So let's do the same for the candidate tower. For now, let's just add the brand, just so that's the first row of the table. It also behaves the same way. So if we have a kind of like a feature imbalance between our two towers, we can already kind of conclude from this example that it has a bad effect on the training and the validation accuracy. But once we started to add more features for the candidate tower, which is sales, profit, and traffic, this is actually when it clicked. Numerical features seem to do the job, and we actually got our validation accuracy up by 4% against baseline model. Additional features, they didn't seem to add much, but they also did not seem to have a negative effect on the training accuracy. In the last row, actually, I had everything for both towers, and we can actually see a small increase in training accuracy. So what we did before, we just worked with embeddings, no nonlinearities. So let's start adding nonlinearities. Just for reference, I have an embedding model with a 64 size for every feature. And for the I use the same features, but in a deep neural network approach. So I add more real layers, I add more dense layers, also with the real activation, and I extend them so I can catch more nonlinearities. And actually, what can I conclude is from this example that having nonlinear activation functions does not do anything good for my results. This is for training, and actually the same for validation. And the validation accuracy for the embedding only type of model is still performing better than dense layers with nonlinear activations. A key insight when working on this project for me was that pre-processing plays a really big role. So previously I had features like gender, like product category, which are not that, let's say, wide in terms of their variation. I used category code encoding or one-hot encoding. So what I tried, first of all, I checked that actually these parameters are not trainable. So the dense layers do learn something from them, but the parameters themselves are not trainable. So what I did, I just put everything into an embedding. I just left the normalized features was normalized because you cannot do anything about it, but the categorical features and one-hot encoded features, I completely embedded everything. And then I actually had a nice additional push in my validation accuracy, and I could also make a further progress with my model. But unfortunately, when I tried the same, again with dense layers with nonlinear activations, my performance went down. So right now, for my experiment, I can conclude that linear activations with a lot of embeddings is the best approach that I could find to train a neural network that is going to generate recommendations. So now let's go to a quick demo of that model. So I'm going to go into Google Colab Pro. I'm going to go quickly load some data. And I'm going to start generating recommendations for random customers. I'm just going to randomly pull a customer from my database. I'm going to display their top 5 history just for reference. So to get an idea like what kind of products did they interact with. By interact, I mean they could buy the product, they could have bought the product. They could also visit the product, just visiting on the webpage. They could add it to a basket, or maybe then remove it, add it to a wish list. So all kinds of possible interactions. So now let's give it a go. So I'm randomly picking a customer, which is not really, let's say, active. It's the customer had bought or interacted somehow with 2 products, which is perfume of the brand Giorgio Armani, and my recommender system recommends more perfume, and predominantly for women. Although the history says actually it was a perfume for men and women, but since it's so sparse, it's really hard maybe to tell. Maybe let's do another example. Let's generate another recommendation. Okay, so this customer actually is more active. So this customer buys woman-man products and gender-neutral products and makeup, but predominantly perfume, and of the brands Paco Rabanne, Gucci, Davidoff. And I'm getting recommendations for that customer for the brand Clinique. Maybe somebody who is more knowledgeable in that field could tell me if that's a good recommendation or not. But at least from the things that I understand, it kind of makes sense. The category, it makes sense. The product gender goes into the same direction. And the brand and the series, for me, doesn't say anything. But it's also possible that some of these products, they have special ingredients or they have a scent that is similar. Because in the end, what I'm doing, I'm feeding all the features that characterize the products into the neural network. So they're possibly utilizing specific similarities. I'm going to make one last run. Maybe somebody in the comment section can tell if these recommendations make sense for them or not. So we're getting, again, more or less gender neutral products. So this client is more or less gender neutral, but who knows if it's a man or a woman, and buys Clinique brand. And actually, I'm recommending to this person also a Clinique brand, but a different series. So there's definitely some kind of similarity happening in the background. And the categories make sense. I have 4 times Pflege, which stands for care. And I'm also recommending predominantly Pflege products. So what else I also want to highlight is an interesting way of generating recommendations with the two-tower neural network that enables you to do that. So I'm just going to go rewind a little bit and say, when you build this network, you feed features into both towers. And that makes this model queryable. So you can actually, the same features that you feed into the model, you can utilize them for the retrieval process. So what I'm going to do now, I'm going to generate recommendations for a random client again. But I'm assuming that this client is in the month of July on the website, and he's just scouting for products. I'm just going to put interaction type visit, just saying visiting for products, and I can generate recommendations based on these features. So I can kind of use like a more sophisticated filtering approach and say, okay, I actually want to generate recommendations for these types of customers. And that could be anything. If I would feed more features like demographics, then I could also generate recommendations based on demographics. I would just have to write several parameters that would do that for me, and that would be just a click of a button as well. So this customer, it gets recommendations for perfume, for predominantly perfume. I can actually also activate to get the history. So we can also view the history, and let's maybe change it as a last example to the month of December, when the seasonality is high. People buy a lot of Christmas products. And see, of course, this is based on the fact if that customer had interacted somehow with anything in December. But for this random customer, there are two examples of interacted products in December, and these are perfume and accessories. And this person also gets recommended perfume of different brands, and gender-wise, looks like a person interested in men products, but is also getting recommendations for women products. So I do assume that this approach might be scrutinized more because of the limitations, because it's like limited in terms of space. It only focuses on specific features, specific values of the features, in this case, the month and the action type. But I would just wanted to showcase you that this kind of approach, this kind of action is possible to work with. So my takeaways from this project, the learnings, especially matrix factorization or deep neural network, like the two-tower neural network with matrix factorization, does not require you to have a prior domain knowledge. I don't have any domain knowledge about beauty products, but I was still able to build a recommender system. So in that sense, it empowers you to work on something that you don't have any specific knowledge about. We heard today the term attention is all you need. I'm gonna throw my version of it. I'm gonna say embeddings is all you need, because embeddings worked for me the best. So the pre-processing part was so important that I embedded everything except continuous variables. And surprisingly, but it was the case with the data that I had, is that linearity was the thing that dominated, that drove my performance of my model forward, and non-linearity actually was having a negative effect. But of course, this is all limited to data, because for future work, to make this model better, we of course need more data, especially more data on the customer and the query tower, because right now there's only 3 features that I used for creating a recommender system. And I utilized only the retrieval approach. There's also a so-called rating approach, but which it basically says that you can optimize against a continuous variable. So I didn't have any continuous variable. A continuous variable would be a rating of a product. I didn't have it in my data, but if it would be supplied, it would be also possible to try this approach. And also one of the more advanced approaches is this DCN, which stands for Deep Cross Network, which is more or less, you can say, is a feature generation thing where you build features, compound features from individual features, and feed those features into the neural network in a more complicated, let's say, architecture. But for that, of course, more time is needed, and also other things. For pictures that I was provided kindly with for the project, I did a couple of experiments, but I could not see anything significant that I can use for my model. But I think it's just really the time limitation I'm pretty sure if the convolutional neural network approach could be explored more with the pictures that I had, there could be some positive effects for the outcome. So this is it. Big thank you very much. Thank you also for the data science retreat, and I hope you enjoyed everybody's presentations today. And it was a really good time. I really enjoyed it. Thank you.